Hi, everyone. My name is Nadezhda Voronova, and I'm going to talk about exponential quantum space advantage for maximum directed cut in the streaming setting. This talk is based on joint work with John Kelleher and Audrey Sparek. This is a talk about quantum computing. Quantum computing is a paradigm of computation that uses the principles of quantum mechanics to process information in ways that are fundamentally different from classical computers. Because of this, we are expecting quantum devices to be much more powerful than classical ones for some tasks. A couple of notable examples of this advantage are Shor's algorithm that solves integer factoring in polynomial time on a quantum device, and Grover's algorithm that allows to do an unstructured search with quadratic speedup using quantum devices. These results motivated a line of work on physically building those quantum devices. In 2023 alone, several groups presented new quantum computers with record number of qubits, which are analogs of bits. Note that, unfortunately, the qubit counts are still very small by classical standards. Moreover, for most of this, the number of qubits displays the total memory that might require error correction since quantum memory is prone to errors. So qubits are still much, much more expensive to implement than bits. This raises a natural question. What can be done with small amount of quantum memory, especially in the era when most of our data is big? Fortunately, we already have a setting that focuses on this exact question. Streaming setting. In the streaming setting, we are designing algorithms for very large data sets where input is given one piece at a time. By very large data sets, we mean they are too large to fit into the memory, while one piece at a time, meaning that the input is given as a sequence of updates. For example, let's say that we are given a huge social network and restricted amount of resources, and this network has to be analyzed while getting updates, while getting this social network as a sequence of updates, like Alice is now friends with Bob, Bob is friends with Charlie, and so on. So in general, we want to analyze some kind of input that is given as a stream with restricted memory. And our goal is to design algorithms that use sublinear memory with respect to the length of the input, and preferably polylogarithmic. The setting can be naturally generalized to the quantum streaming setting. In the quantum streaming setting, the device analyzing the stream is assumed to be a quantum computer. So the algorithm is allowed to store a quantum state, and our goal is to design algorithms that use small amount of memory. Quantum streaming setting allows us to prove an unconditional quantum advantage, since one can prove unconditional lower bounds in the classical setting. Moreover, this setting allows us to analyze how to use the quantum memory efficiently for tasks that fit into the streaming setting naturally. And since quantum memory is much more expensive than classical memory, we would like to maximize the advantage we get from using quantum computers. Because of this, we are interested in finding exponential quantum space advantage for a streaming problem that people care about. Let's look at the state of the art for this. Several work showed that exponential quantum space advantage is achievable in the streaming setting, but unfortunately, the problems considered there were designed specifically to show this operation and have not been considered in the streaming setting outside of those works. Other works showed quantum advantage for very natural problems of moment estimation and triangle counting, but these works did not achieve exponential quantum advantage in one-pass setting. In this work, we show exponential quantum advantage for a very natural problem of approximating the value of maximum directed cut in the streaming setting. Note that for a very similar problem of approximating maximum cut, it has been proven that no quantum advantage, even polynomial, is possible. So what is this maximum directed cut problem? In the maximum directed cut problem, we're given a directed graph on n vertices, and our goal is to find a partition of vertices into two sets, blue and orange on the screen, such that the number of edges that go from the blue set to orange set is maximized. Note that in this work, we are only interested in outputting the value of the maximum directed cut and not the cut itself. This problem is NP hard. So for the rest of the talk, we're going to focus on approximating the value of maximum directed cut. Under unique games conjecture, there exists an approximation factor alpha, such that approximating up to this approximation factor is durable in polynomial time, while any better approximation is NP hard. And it's known that 0.874 approximation is achievable in polynomial time in the RAM setting, which is less restrictive than the streaming setting. In the streaming setting, the graph is given as a sequence of directed edges given in arbitrary order. And as a reminder, our goal is to design an algorithm that approximates the value of maximum directed cut in restricted space. Let's see what is possible for this problem. Note that 1/4 approximation is trivial, since a random partition cuts 1/4 of edges. It was shown that any approximation better than 1/2 requires linear memory, both in the classical and quantum setting. It was also shown that 4/9 approximation is achievable in Paul logarithmic number of classical bits, and any approximation better than 4/9 requires square root of n classical bits. Note that this lower bound does not generalize to the quantum setting. This bound was shown to be tight for approximation up to 484 factor, and we show that the same approximation factor is achievable in Paul logarithmic number of qubits, which gives us the exponential advantage. Our approximation factor is the same because we are approximating the same set of statistics about the graph as Saxena, Singers, Sudan, and Velusamy do. This set of statistics is called a snapshot. Let's say that our vertices are split up into some number of buckets, and the snapshot with respect to this partition is a succinct representation of this graph that counts the number of edges that go from vertices of one bucket to another. The reason why this set of statistics is interesting is because there is a way to split the vertices into some buckets in a way that a snapshot with respect to those buckets is sufficient for 0.484 approximation of maximum directed cut. These buckets depend on the biases of vertices. A bias of a vertex is the difference between its out and in degree normalized by its total degree. Note that this value is always somewhere between -1 and 1. And let's say that someone has given us a way to partition this interval into constant number of bias classes. Then we can partition the vertices of a graph with respect to this partition of biases into constant number of bias classes. And then a snapshot is basically a histogram of the number of edges that go from vertices of one bias class to another. It was shown that there is a way to split up biases into constant number of bias classes in a way that the snapshot is sufficient for 0.484 approximation of maximum directed cut. This result was used in the upper bound, square root of n classical upper bound, where the authors showed that an approximation of a snapshot is computable in square root of n memory, and this approximation is sufficient for the previous result to go through. We show that a different approximation of the same snapshot is computable in polylogarithmic number of qubits, and is still sufficient for 0.484 approximation of maximum directed cut. Note that in order to solve this problem of computing a snapshot, it is essential to be able to compute the number of edges incident to vertices with some specific properties. In our case, belonging to a specific pair of bias classes. This subproblem can be worded as follows. Let's say that we have some universe U, and we're given a set T of elements from this universe. And our goal is to design a small sketch that solves the following problem. If we're given a set of disjoint pairs P of elements from the universe, we want to estimate the number of elements, the number of pairs that fully lie in T. Note that we can do this classically by subsampling square root of size of T elements by Bird paradox. And it can be shown then that this is optimal by reduction from Boolean hidden matching. In the same work on Boolean hidden matching, it was shown that this problem can be solved in just polylogarithmic space with respect to the size of T on a quantum device. And in our algorithm, we built on this quantum sketch in order to approximate the snapshot and thus the maximum directed cut. By doing this, we show that there exists a quantum streaming algorithm that 0.484 approximates the value of maximum directed cut in polylogarithmic space. And this, to the best of our knowledge, shows the first exponential quantum space advantage for a natural problem in the streaming setting. And to conclude, a couple of open problems. The first one is to understand the quantum streaming complexity of maximum directed cut. Since we showed that 0.484 approximation is doable in just polylogarithmic space, and it was known that any approximation better than 1/2 requires linear space, there is a gap between those two factors, and it would be interesting to understand what's going on there. The second one is to characterize which CSPs allow quantum advantage and which do not. We show that maximum directed cut allows exponential quantum streaming advantage, while an undirected version of this problem, maximum cut, does not allow any quantum advantage whatsoever. How can we characterize which CSPs allow some quantum advantage and exponential quantum advantage and which do not? And the last one is understanding the quantum advantage for approximation problems. Search for quantum advantage for approximating NP-hard discrete optimization problems has been an active area of research for the last decade, while the results have been pretty modest. Our work shows that under a restricted input model, such quantum approximation advantages are possible. Could it be that we are overlooking some critical quantum advantages because we are biased towards certain kinds of problems or input models? And that's it. Thank you for your time.